Good evening, everyone. Am I audible?
Yes, ma'am.
Can you hear me?
Hello.
Okay. So, give me 2 minutes.
Yeah.
We'll start the session.
Okay.
So, let's start today's session. So, in today's session, we are going to see topics from week 8. Okay. So, in week 8, we are going to mainly look at the topic of conditional probability. So, I guess you all remember what is mean by a contingency table. So the first three topics we will see mainly based on a contingency table. Okay. And then based on the topics we have seen like joint probability, marginal probability, and conditional probability from the first three topics. So the remaining topics, we can see the relations, and at last we will see the important rule, which is called the Bayes rule. So these are the topics we are going to see today. Okay, so we'll start with what is called joint probability. So in the previous week, you are already introduced with the basic properties of probability and all. So now we will see what is called joint probability. Okay. All right. So what is joint probability? Joint probability, so as the name suggests, is the probability that two or more events happens at the same time. Okay. So if you look at the contingency table, so each cell gives you a joint probability. What does that mean? So suppose let us say you have two events A and B. These are the two events. Okay. What is mean by joint probability of these two events? It is P of A intersection B. That is probability of A intersection B. Okay. So to understand what is joint probability, let us look at an example. Suppose you roll a fair die once. Okay. Now let A be the event of getting an even number and B be the event of getting a number greater than 3. Now what is joint probability P of A intersection B? You can do this without a contingency table also, but here specifically I am doing it with a contingency table so that you can relate with the next example. Okay, so this example can be done without a contingency table also. So how can you do this without a contingency table? So first of all, what are all the elements there in the set A? Yeah. What are all the numbers which are even number when you roll a fair die?
Ma'am, 246.
Yes. So here you see, here we have 2, 4, 6. These are the possible outcomes, right? And what about B?
And 456.
4, 5, 6, right? So here, total number of outcomes. What is the total number of outcomes? What is the total number of outcomes? Yeah,
6.
six, right? So what should be the probability of A intersection B then? So what is there in A intersection B?
And 4 and 6.
4 and 6. So what is the probability of A intersection B? So number of possible events in A intersection B by total number of outcomes, right? So what is that?
2 by 6.
2 by 6, right? So this is the joint probability. So here, if we want to make it from a contingency table also, we can do that. How is it done? So in the case of contingency table, you can observe joint probability of more than one event, not just A intersection B. You can also see A intersection B complement. You can also see A complement intersection B. You can also see A complement intersection B complement. Everything is possible here, right? So as we already saw, so here, how many elements are going to be there in A as well as B? You know that here in A and B, you have 2, right? So these are the 2 elements, 4 and 6. And what is there in A but not in B? What is there in, how many elements are there in A but not B? Which element is there? 2, 4, 6. Out of 2, 4, 6, which element is there in B that we should remove? 4 and 6 are there in B. So we cannot take 4 and 6 from A, right? So only 2. So how many elements? Only 1 element, right? So which is 1. So here the entries are 4 and 6. Here the entry is just 2. Can you say what is the entry here? Which is in B but not in A. It should not be in A.
Five.
5. Okay, then entry 5, yes, yeah. So here again, only 1 element. Okay. What about here in this place? It should not be in A and not in B as well. What are, how many entries are there? Not in A as well as B. What are those entries?
Two and 5.
What are the entries?
2 and 5.
1 and 3, right? It should not be in A as well as in B.
Okay.
So here again, only 2 entries. Yeah. All right. So here you see this is in this place, it is kind of representing A intersection B. And this represents, can you say what is this representing? What is this representing, this place? A intersection with B complement. Right? A intersection with B complement. Similarly, can you say what is this representing? What is this representing?
A complement section.
A complement intersection B. Right? Okay. Here at the last,
A complement intersection complement.
okay. So now, what are the joint probabilities? The joint probabilities, it is not just the numbers, but the probabilities. So here You see, this is probability of A intersection B. This is probability of A intersection B complement. This is probability of A complement intersection B. And this is the probability of A complement intersection B complement. Okay, fine. Now let us see another example here. So this is the example from the lecture. So here you see that. So now this is a data represented in a contingency table where whether a person owns a smartphone or not based on the gender. So this classification is given in a contingency table. Okay. So now here we also have the row total and column total in each case. Okay. So now to get the probabilities, we have to divide by 100 because that is the total. Right. So this is the total, overall total. So to get the probability, we are dividing each of these entries by 100. Okay. Now what are these representing? So here, what are the joint probabilities? Each of this is now a joint probability. Okay, so each of this cell is now a joint probability, just like we saw in the previous case. Now, what are those representing? So, for example, if you take the first one, probability of female and not owning a smartphone. So, which one is representing this probability? What is the probability of this particular event? Female and not owning a smartphone. Yeah. See, here this is representing, this row is representing female, right? And the first column represents the people who are not owning a smartphone. So this is the intersection, this 0.10 is the intersection of female who are not owning, right? So in that case, what is the first probability? 0.10. Okay. Now, can you say probability of female and owning a smartphone? Yeah. 0.34. Very good. What about probability of male and not owning a smartphone?
0.14.
0.14. Okay. Probability of male and owning a smartphone?
0.42.
0.42. So you see that we have 4 cells and each of these cells is representing a probability. Here you see it is mentioned in terms of and. So previously we were seeing it in terms of intersection. So just to have a relation between what we saw earlier and this one. So for example, let us say the females are represented with A, males are represented with B. Okay. And those who are owning a smartphone, let us say, not owning a smartphone, let us say probability of not owning a smartphone, probability of owning a smartphone. Okay. So now for the first one represents probability of A intersection NS. Right. Maybe I should simply write NS and OS. Not owning a smartphone, owning a smartphone. Okay, A intersection NS. What is the second one representing? Probability of the second one. A intersection.
A intersection means owning.
Yeah. So similarly, probability of B intersection NS and probability of B intersection OS. So all these are joint probabilities. Okay. All right. So the next one is marginal probability. So just like the name marginal, you can guess that earlier joint probability means it is representing something together, right? Now marginal means something should be there in the margin, but which margin? Okay, so let's try to understand. So marginal probability is the probability of a single event ignoring the other variables. What does this mean? It is obtained by summing or adding joint probabilities over the other variables. What does that mean? So suppose here, for example, the same example which we considered earlier. So where A is getting an even number when rolling a die and B is the event of getting a number greater than 3. The same example. Okay, so this is the table we had, the contingency table. So now what is the marginal probability? How do we get it? So they are the row totals and column totals. So what is the row total here? What is the row total here? First row
6.
total 3 by 6. Okay, first row total is 3 by 6, which is 1 by 2. Okay, so 2 by 6 plus 1 by 6 is 3 by 6, 1 by 2. Similarly, here 1 by 6 plus 2 by 6 is again 3 by 6, which is 1 by 2. So these are row totals. And what are the column totals? The same, right? So 2 by 6 plus 1 by 6 here again 3 by 6. So which is 1 by 2. Similarly, here also 1 by 2. Okay. So in this particular example, the row totals and column totals come up to be the same. Okay. So they are representing the same. Okay. Now, what are the marginal probability here? So the marginal probability is probability of just A. If you want to see, what is the probability of just A? So here we know that A is actually having 2, 4, 6. These are the elements. So what is probability of A actually? 3 by 6. That you can see in the first column, first row sum. The first row sum gives you this probability. Same way, A complement, you know, there are 1, 3 and 5. So again, you see A complement, probability of A complement is given here. So this is probability of A. This is probability of complement. And this is probability of B. And this is probability of B complement. Okay. So here all these values are same. Just 1 by 2, 1 by 2, 1 by 2. So here also 1 by 2. Okay, so what are the marginal probabilities? The row sums and column sums are the marginal probabilities. Okay, so here we are just considering only one element. For example, only A, and we are not looking about the event B. When we are looking at the first row sum. Similarly, if you take the first column sum, we are looking at only the event B and not the event A at all. Okay, so here in the next example, so the previous example which we have taken. Sorry. So here in this example, so if you consider this case, here also we have 4 marginal probabilities because we have 2 row sums and 2 column sums, right? So in this particular case, can you say what is the probability of female? How many females are there in total? And what is the probability of a person being a female in this scenario?
0.44.
0.44. Similarly, what is the probability of male?
0.56.
0.56. Probability of not owning a smartphone, irrespective of the gender.
0.24.
And probability of owning a smartphone,
0.76.
is so. Put a point here. Okay. So one thing you can note that the row sum and column sum, if you add them up, it is 1. It should be 1. All right. Okay. Now the next topic is conditional probability. So conditional probability is the probability of an event given another event has already happened. So what did we saw in marginal probability? In marginal probability, we were considering only one event and neglecting the other one, right? We are not considering the other one at all. But when we are looking at conditional probability, we are assuming that one event has already happened. In that scenario, what is the probability of other event also to happen? This is conditional probability. Okay. So we are given that certain event is already happening, and in that condition, what is the probability of the other event? Okay. So for example, what is this P of A given B means? Given that the event B is already happening, what is the happened? What is the probability of A? So given the event B happened, what is the probability of A? So this is probability. How do you read this? Probability of A given B. So you read it as A given B. Okay, fine. So how to understand this? Let's see with an example. Now the same event let us consider. So the first example, A getting an even number, B getting a number greater than 1. Now what is the probability of the event A given B? It means already we know that the event B has happened. So it means we already know that the outcome is greater than 3. Now, what is the probability of A? You understand what is the question? Yeah. So what is the answer? Can anyone tell me the answer? This is a simple question. So you know that here you have the numbers 2, 4 and 6, right? And here you are having numbers greater than 6. So the thing is that now they are given that the outcome is already greater than 3. So given B. So it means the outcome is already greater than 3. In that, what is the probability of the event A? What is the outcome? So greater than 3 and it is an even number. So what are the possible chances?
4 and 6.
Exactly. Right? So you have two events. So what should be the probability?
2/6.
This is where you make the mistake. Okay. So the thing is that you are still considering the sample space as the entire sample space, right? 1, 2, 3, 4, 5, 6. But now here your sample space is not the entire space because you are given B. It means if we are told B has already happened, then the possible outcomes are no longer all the 6 outcomes. Now the new sample space is just 4, 5, and 6. Right? Now, out of this 3, you are now getting 4 or 6. So, out of 3, you have 2 chances. So, now, can you update the answer? What should be the answer?
2/3.
By 3.
Exactly. Okay. So, here you see that find where A also happens. So, from this sample space, you know that the even numbers are 4 and 6. So, the probability of A given B is favorable outcomes by possible outcomes. So, you have number of course. So, you have 2 by B. Okay. Is it making sense? Okay. So, this is how you should understand probability of A given B. Okay. Now, there is a formula for conditional probability. This is called conditional probability and this is given by this formula. Okay. So you can relate it with what we have done earlier. So what we have done earlier? So we were first looking at, so here this is just B, the number of entries of B, right? And here, what is this 4, 6 actually representing? So this is your samples, this is actually your set B. And what is this? So this is A intersection B. Is that correct? This is A intersection B. So, this probability of A given B can be written as probability of A intersection B by probability of B. So, if you apply this formula in the previous scenario, what will you get? So probability of A intersection B is actually 2 by 6, right? And what is probability of B? 3 by 6, right? So now what is probability of A given B using this formula? 2 by 6 by 3 by 6. So again, you are getting 2 by 3. Okay. So either you can understand it directly and do it, or you use this formula. Both should give the same answer. Okay. So far, the conditional probability, is it clear? Okay. Let's try to understand it better with another example here. Now let's continue with the same example we considered earlier. Now find the conditional probabilities to answer questions like, so what is this question? Among female buyers. So what is given to you among female buyers? So this is what is the first condition. What is the chance someone owns a phone? Okay, what is the chance someone owns a phone? So what can be the answer for this in this case? So here, let's say that the same notation, let us have like we mentioned earlier, maybe A, B, and not owning a smartphone, owning a smartphone. Okay, so what is the notation you have to write here? Can someone say? So what is given? So this is the given condition. Okay, and what is that we need to find? What is the chance someone owns a phone? So what is that we actually have to find here?
P of A intersection OS by P of A.
A intersection
OS madam.
OS
Yeah, divided by P of A.
divided by P of A, right? So in terms of conditional probability, this is exactly what? This is probability of OS given, right? Probability of OS given A. Good. Right? Now what is this P of A intersection OS in this case?
0.34.
Yeah. And what is probability of A?
0.44.
0.4. Okay, you can simplify and get the answer. Okay, same way. Now we have another question. Among people who don't own a phone, how many are male? So now what is given to you? So this is given. Now we are only considering people who don't own a phone. In that, how many are male? So what is that we need to find here? What is that we need to find? We need to find probability of
P of N is over B.
not owning phone. Is this what should come here?
Over
What
B.
should come here? Are you sure?
No, no, here it should be
Okay.
probability of male.
Male.
Probability of male
Male, so B.
given
Given
not owning a
NS.
N.
not owning a smart. Okay. So here this is nothing but probability of B intersection NS by probability of NS. So what is your given? That it should be clear. Then you can easily write the conditional probability. Okay, given is not owning a smartphone, right? So what should be the answer here? Probability of B intersection NS. What is probability of B intersection NS?
0.14.
0.14.
B intersection NS is 0.14, yes. And what is probability of NS?
0.24.
0.
Okay. So now what is conditional probability? Is that clear for everyone? Yeah?
Yes, ma'am.
Okay. Now let us look at another
Uh,
example here. Yes?
Sorry, ma'am.
Any
No.
questions?
Yeah, ma'am. Actually, can you just go above? So here, yeah. So sorry. So here, among people who don't own a phone, it is a generic, right? For a female and male.
Hmm.
And then they are saying how many are male.
Yes.
So among the people who don't own phone, then it should be combined, right? For male and female both. Why we are just taking for male over here?
See, now what is the updated sample space? That is what is the first thing. Among people who don't own a phone. So now the new sample space is people not owning phone. Right? So how many are not owning a phone? So you see there are 24 people who don't own a phone. Okay. So there are 24 people who don't own a phone. And out of that, they are asking how many are male. Out of 24, how many are male?
Yeah, 14.
14?
Yeah.
Oh,
Thank you.
okay. Shall we move on?
Yes, ma'am.
Oh, so now let's look at the next example. Okay. So now this is a common example you take. Roll a dice twice. So in that case, you know that this is the sample space. Right? So you know that what is the total number of elements in this sample space?
36.
36. So the number of elements in S is 36. Okay. So now each outcome is equally likely to occur with the probability of what's the answer?
1 by
1 by
36.
36.
1 by 30. Okay. Now suppose further that the first roll of the dice lands on 2. Okay. So now the first roll, we know that it is landing on 2. Okay. Now, given this information, what is the resulting probability that the sum of the dice is 6? Okay. Just think about this.
One by 6, madam.
1 by 6.
1 by 6.
Ma'am, 5 by 30.
Yeah, it's 1 by 6. Why? Because suppose if we are denoting the event of, okay, so here we are denoting E, which is the event of getting the sum of the dice is 6, and F is the event of getting the die where the first entry is 2, right? So in here for F, how many entries are there, and E, how many entries are there? What are the entries in E and what are the entries in F? So first let's say about F. What are the entries in F?
2 1 2 2 2 3 2 4 2 5 2 6.
So this is actually now our updated sample space, right? Because this is the first condition given, right? Now they are saying that, so E is the event where the sum of the dice is 6. So what are the entries there in E? What are the entries there in E?
Two comma
4.
4.
So you are saying E intersection F. Just in E, what are there?
Okay.
2
Comma 5.
2
3.
comma 4.
2 comma 4.
3 comma 3. 4 comma 2. 5 comma 2. Sorry, 5 comma 1.
Okay. So these are the entries. Okay. Now we are asked to find what is probability of E given F. Right? That is the question. Right? So if it is E given F, we know that it is probability of E intersection F by probability of F. Right? Now E intersection F, what is there in E intersection F?
2 comma 4.
2 comma 4. So we know that here it should be 1 by 36 and here also not 1. So 6 by 36. So the answer is 1 by 6. So if you use the formula, this is the way. Or if you want just to say that F is the sample space and then out of this, which one is having a sum 6? So only one entry, which is this. So directly 1 out of 6. That way also you can answer. Okay, either way you can see that the answer is 1 by 6. Okay. Fine. All right. Okay. So now the next thing we are going to see is called the multiplication rule. Okay. So what is this multiplication rule? So we know that this is the conditional probability formula. P of E given F is P of E intersection F by P of F. Now, if we are multiplying P of F on both sides, then what is that we are getting? P of E intersection F is equal to P of F. Actually, this goes here. P of F into P of E given F. So, if you want to find the intersection, sometimes this multiplication rule is useful. So, you see that sometimes the data does not tell you what is there in the intersection, but it tells you this probability. In that case, you can use this multiplication rule to find the probability of E intersection F. Okay, we will see some examples to see where this formula is going to be useful. Okay, so what is this rule saying? That the probability that both E and F can occur is equal to probability of F multiplied by the conditional probability of E given F occurs. Okay, fine. So let's see an example. In an introductory statistics class of 40 students, the number of males is equal to 23 and the number of females is equal to 17. So what is the total count of students?
40.
Okay, out of that you have males 23. So if you have denote B, okay, so maybe first we'll not do this. So male is 23, total males is 23 and total females is 17. Now, 2 students are selected at random from the class. Okay, so some 2 students are selected and the sampling is done without replacement. Okay, so they are not replacing anyone after picking the student first student. They are not replacing anyone and then they are choosing the second one. Now the question is, find the probability that the first student is female and the second is male. Okay, so what is that we need to find? We need to find that the first student is female and the second is male. So how to find this? So first we are going to define the events. So A is the event that the first student is female and B is the event where the second student is male. So if A is this and B is this, what is that we need to find? What is that we need to find?
Probability of A.
A and then see, and we are having first student selected as female and the second is male. This is what we need to find. So what is that we need to find? Probability of A intersection B, right? Both needs to happen. First should be female and also the second should be the male. Both should happen, right? So we need to find probability of A intersection B. Is that first of all clear for everyone that we need to find P of A intersection B here? Yes? Is that
Yes,
part clear
madam.
for everyone?
Mm.
Okay. Okay. Now, if we have to find probability of A intersection B, now the hint is that we are going to use this multiplication rule. How are we going to use the multiplication rule? What is the multiplication rule saying first of all? What is the multiplication rule saying? P of A intersection B is, if you want, you can check it from here. What should be the answer? P of A intersection B is
P of A over B into P of B.
P of B into P
P
of
of A over B.
A given B. So P of A given B. So this is what we are going to do. Now, what is that we need to find here? First, we have to compute each part from here. Okay. So how are we going to compute each part? So, okay. So here they are going to use the other way around. So in this way also we can find. So we can do it this way or that way. Either way it's correct only. So here they are using A and B given A. Okay. So probability that the first student is male, because we are choosing the first student, right? And then only second student. So given first student is male makes sense. That's why they are using this formula. Okay, so if you are using this formula, then what is P of A?
Madam, your voice is not audible.
17 by 40.
Can you hear me now?
Yes, ma'am.
Yeah. What is P of A now?
17 by 40.
17 by 40. All right. Now you see that the sampling is without replacement.
Without.
Yeah. So now probability of second student is male given the first was female. What is P of B given A?
23 by 39.
How much?
23 by 39.
23 by 30.
Very 39. Very good. Because the total count reduces to 1, but the number of males remains the same. Because the first student is a female, the male count remains the same. So it should be 23 by 39. Okay. So now the total students left is 39 and the males are 23. So it is 23 by 39. So probability of B given A is 23 by 39. And if we apply the formula now, what should be the answer? If you apply the formula,
17 by
17 by
40 multiplied
40
23 by
into
20.
23 by 30.
39.
you can do the calculations and see what is the answer you are getting. Okay. So the logic behind this, is it clear? How we are finding the answer here, is it clear for everyone?
Yes,
Yes,
madam, one doubt.
Yeah.
Like, can we solve this also in the way like using the combination formula, like 17C1 into 23C1
Yes,
divided
yes.
by 40C2?
Yes, yes, that is also possible. Yeah.
Okay.
All right. So now you see that if we have two events, we know what is the multiplication rule. The multiplication rule says that P of A into P of B given A. Right? So this is the multiplication rule for two variables. Suppose we are having three events, then what is the generalized multiplication rule? Okay. So here first we will see for three events and then we can generalize it for more than three events. Okay. In general, n events also we can do. Okay. So how can we do this? So for example, suppose we have three events A, B and C. Okay. So now we have to find P of A intersection B intersection C and we have to give a multiplication rule for this. What is the multiplication rule? Now let us consider this A intersection B as one event. Okay. So now you have P of A intersection B intersection C. Okay. So now in this case, so if A intersection B is one event, then how can you write P of A intersection B intersection C? See, maybe you give some name for this is D. Then what is this? P of D intersection C is equal to, based on the above formula you have. Use this formula. It is, I'm audible, right? Is my
P
question
of
clear?
D given C into P of C.
Yes, ma'am.
P of D into P of C given D. Right? Now what is D? D is nothing but A intersection B. And this is P of C given A intersection B. Right? Now again, according to the multiplication rule, what is P of A intersection B?
P of A into B, B is
Okay. So your multiplication rule for three events is like this. P of A intersection B intersection C is equal to P of A into P of B given A into P of C given A intersection B. Okay, so the multiplication rule for 3 events goes like this. If this is the multiplication rule for 3 events, what should be the multiplication rule for n events? Suppose you have events like A1, A2, AN. What should be P of A1 intersection A2 intersection etc. AN? Can anyone guess? Maybe can you try for maybe 4 events first of all? What is the probability of A1 intersection, A2 intersection, A3 intersection, A4? Can you try? Yes. Okay, maybe I'll start. So it should be P of A1, right? And then P of A2 given A1. And then what? What should be?
Probability of A3.
A3 given A1 intersection A.
And then
Then A4 A1 intersection
A1 intersection A2
A2
intersection
intersection
A3.
A3.
okay, so this is for
And-
4 events, right? So now you know that the general formula should go like this. So if you have n events, the joint probability is given as follows. So how are we getting the joint probability of n events? Is that clear for everyone? Yeah?
Yeah.
Yes. Okay. So now let's see an example where we can use this multiplication rule. Okay. All right. Now here the question is, an ordinary deck of 52 playing cards is randomly divided into 4 piles of 13 cards each. Okay. Now compute the probability that each pile has exactly 1 king. So first of all, how many kings are there in a pack of 52 cards?
4.
4. There are 4 kings. Right? Now we are going to use the multiplication rule we just saw. So in that case, so I'm going to divide it in this way. So I'm going to have 4 events in this way. So here this spade, heart, diamonds, and all this you can interchange with any order you want. This order does not have any specific reason. Maybe for example, you can start with hearts or diamonds or anything. Okay, so this is just something you are starting with, that's all. And then you are fixing first, you are fixing 1, and then you are fixing 2, and then fixing 3. So what are they? The order does not matter. Okay, so you have 4 different symbols. So those 4 different symbols you are using in some order here. Okay, so here specifically, for example, E1 represents the event of having a king of spades in some pile. Okay, so and E2 represents the event of having king of spades and hearts in different pile. Now E3 is the event of having kings of spades, hearts, and diamonds, all of the 3 in different piles. Now E4, all 4 kings are in different piles. Okay, so now the question is asking what is the probability that each pile has exactly 1 king. Okay, so it means all 4 kings should be in different piles. That is what we are looking for, right? So first of all, let's first try to understand E1. What is E1? The king has to be in any one pile. Will the king be there in any one pile? King of spades, will it be there in any one pile?
Yes, madam.
It is obvious, right? So what should be the probability of E1 then?
1 by 52.
So will it happen with any condition? So is there any doubt in this? King of spades is in some pile. Is there any question about this?
No.
There is no question. So there is no probability. So what should be the probability in that case? If you are sure that the event will
One.
happen, 1.
Then it's
If you are sure that the event will happen, you know that the probability is 1. Right? Okay. So if probability of E1 is 1, the next thing is understanding probability of E2. Now what is E2? So E2 is the kings of spades and hearts now are in different piles. So what does that mean? Now first something
Ma'am?
is already, yes,
Please explain event 1 again.
yes. So now you have spade. So the spade, I don't know. So this king of spade, okay, is, so now you have totally 4 piles. So the 52 cards are divided into 4 piles. Pile 1, pile 2, pile 3, pile 4. So 4 different categories it is split in. Now each of this is having 13 cards. Now this card must be there in any one pile, correct? Yes or no?
Yes, ma'am.
That is for sure, right? This card will be there in any one pile, that is for sure, right? Yeah. So
Yes, ma'am.
event is the event of having this particular card in any one of this pile. And that is for sure. And hence probability of E1 is 1. Now is that making sense? Yes or no? Yeah? Or still is it not clear?
Yes, ma'am.
Not clear.
Yes, ma'am. It's not clear.
Okay. See, what is E1? E1 is the event of king of spade in any one of this pile. Okay. So king of spade is going to be either in P1 or P2 or P3 or P4. Now, what
Yes,
is the
ma'am.
probability that this king is there in any one of this pile? Probability means the chances. With that 100%, you know that it is going to be there in any one of this pile. Yes or no?
Yes, ma'am.
100% means what is the probability?
Yes, ma'am.
1.
Okay,
Right?
ma'am. Yes, ma'am. Right. Thank you,
Okay.
ma'am.
Okay. Now you see that what is that we have to find? We have to find the probability that each pile has exactly 1 king. That is, all 4 kings are in different piles. This is what we need to find. Right? Basically, we need to find P of E4. But there is something to note. What is that P of E4 represents? P of E4 is equal to P of E1 intersection E2 intersection E3 intersection E4. How many of you can understand this? Why is P of E4 equal to all this? Is it making sense? Is it making sense why it is equal? Okay, so let's maybe try to understand that. So what is happening? If all 4 kings are in different piles, does it guarantee that the first 3 kings are in different piles? E4
No, madam.
implies
They
E3.
can be in one pile also.
No. The thing is that all 4 kings are in different piles. This is given.
Yes.
If this is given, then you know that the first 3 kings are in different piles, right? You already know all of them are in different
Yeah,
piles.
correct. Okay.
Then E4 implies E3. And if you know that first 3 kings are in different piles, you know that the first 2 kings must also be in 2 different piles.
Yes.
Same way, you know that the first one is always true. Without any of this is always true. So this means that if E4 happens, then automatically E3, E2, E1 is happening. Right? So this means what? We are having nested events. So E4 happens means E3 happens, E2 happens, and E1 happens. So in that case, E1 intersection E2 intersection E3 intersection E4 is E4. So why is this true? Is that making sense now? Is it clear for everyone now?
Yes, madam.
Okay. Okay. So now we have to find P of E4. So instead of P of E4 is actually P of E1 intersection E2 intersection E3 intersection E4. It means what is the rule we can apply here? We can use multiplication rule. So can anyone try to tell the multiplication rule here. What is the multiplication rule? P of E1 into
Multiplied by P of E1 over E2 given E2. P of E2 given
E2 given
Intersection of E1, E2.
So first of all, here it is P of E1 given E2, or what is that? Is that correct? Go
No.
back here and see.
E2 by E1
Yeah. Here it is E2 given
by E1.
E1 and then
Probability of E2.
E3
Oh, yes, ma'am. Probability
E1
of
intersection E2.
E1 intersection E2. Probability of E4. Probability of E1 intersection E2 intersection E3.
Okay, so this is the formula we are going to use. Out of this, now we know that the first value is 1, right? Probability of E1 is 1, right? So the next thing we have to look at is probability of E2 given E1. So E1 is anyway obviously true. Now we are going to see that E2, probability of E2 given E1. That is, king of spades and hearts are in different piles. So how to understand this? That the king of heart and spade are in different piles. So first we need to fix something, right? So here, so this one we saw it is 1. Now we have to understand P of E2 given E1. So maybe we have to fix any one. Either we have to fix the spade or heart. So if we are suppose fixing spade in one pile, okay. So how many plays of, so what is the total number of positions you have now for the next one? So already 1 is fixed. Okay, 1
3.
card. No. Possible positions for the next card.
The other 3 piles, madam.
No, for heart, for king of, for this particular card, for king of hearts, how many possible boxes you have? So beginning, how many
boxes.
were? No. So total, when we started, total how many were there? Total how many cards when we started?
52 cards.
52. Now out of that, 1 card is fixed. Now for the king of hearts, it can take how many possible positions?
51.
51 positions. Now if suppose let us say this is in some pile, okay? Now in that pile, so how many positions do you have? Suppose you are considering, let's say king of spade is in some pile Pi. Okay, in the same pile, how many positions do you have for the king of hearts?
12.
Yes, exactly. So, but we want the king of heart in a different pile. So different pile, how many positions? How do you find? 51 minus 12.
12.
So how many?
39.
39. Is this clear for everyone? So the total positions is 51. If you are looking at the same pile as that of spades, there are 12, but you want it in a different pile. So it means there are 39 positions, 51 minus 12. Up to this, is it clear for everyone? Yeah? Okay. Now, what is probability of E2 given E1? In the updated sample space, you have the number of position is 51. And for E2 and for spade and heart to be in different, so different pile positions, there are 39. So it is 39 by 51. Is it making sense for everyone? Is it clear why it is 39 by 51?
Yes.
No? Okay. Fine. So the next thing we need to see is what is P of E3 given E1 intersection E2. Okay. What is P of E3 given E1 intersection E2? What is E1 intersection E2, by the way? It is same as E2. Right? Because of this conditions we have here. Right? So because of this E1 intersection E2 is E2. So it is just P of E3 given E2. Okay. Now already we know that two kings are in different piles. Right? So now how many positions are remaining for us for the king of diamonds?
50.
50. Now, what is the possibility that the same two piles, suppose if it is there in going to take the same two piles? So
11.
no. So the first two are in different piles, remember that. So first pile, so let's say Pi and Pj. So let's say your spade is here and heart is here. Okay. So now out of this one is taken, out of this one is taken. So how many are there in the same two piles?
12 into 12.
Pi plus Pj. Right? Total number of positions only, y into.
Okay, right.
Okay. And so what is the possibility of different positions? So different positions means different pile positions here they are saying. They are in different piles. So if they are in different piles, then here you have two more piles, right? So how many possible places are there? 50 minus 24. What is that?
36.
26.
26. Yes.
Right? So in this case, what is P of E3 given E2? E3 given E2 is 26 by 50. Is this clear? So now all the three cards, spade, heart and diamond, all of them now are in different piles. So the different pile positions are 26 given the total position is 50. Okay. So the next thing we have to find is this value. So now again, this is same as E3 because of the same condition here. Okay. So now we are going to find what is P of E4 given E3. Now for P4 given E3, you are going to tell everything. I will not give because already you have enough chances to understand what is that we need to do. So I want all of you to try it yourself. So what is the total number of positions? Already three kings are
49, madam. 49.
very good. So now if say not two, same three piles. So if they are in the same three piles, then so let's say Pi, Pj and Pk. So in each there are 12, 12, 12. So
36.
36. So what are the possibility for different pile position?
49 minus 36.
Okay. So now what should be probability of E4 given E3?
13 by 49.
13 by 14. Okay. So now multiply all probabilities. Probability of E4 is probability of E1 into probability of E2 given E1 into probability of E3 given E1 intersection E2, which is same as E2. So maybe I'll write simply E2 and to probability of E4 given E3. So 1 into what was the value we had? 39 by 51. And then 26 by 50. And then 13 by 40. So you can do the calculations and write the answer. So is this question clear for everyone? Any questions here? So this question, is it clear for everyone? How did we find all four kings in different piles? Is it clear for everyone? Shall we move on?
Yes.
Okay. Okay, good. Okay, so the next topic is understanding what are independent events. Okay, so it means that what is meant by independent? So the name, what does it suggest? The name suggests that if there are two events, the happening of one event should not be dependent on the other event. Okay, so both should happen independent. So in terms of conditional probability, how to understand this? So the question comes like this. Well, the conditional probability that E occurs given F. Okay, so now you have the condition that F has happened. Now they are asking what is the probability of E. So does it have any effect or is it just probability of E? Okay, does the event F has any effect or is it just probability of E? So the question is P of E given F same as P of E? So it means does F has any effect on E? Roughly, this is the question, right? So this means we are asking is P of E given F equal to E? So that is what we say as E is independent of F. Okay. So in other words, event E is independent of F if knowing whether F occurs does not affect the probability of E. Okay. So how to write this in terms of formula? So you see that we already know from multiplication rule that P of E intersection F is P of F into P of E given F. Okay. If E is independent of F, then this P of E given F is same as P of E. So your P of E intersection F simply turns out to be P of F into P of E. Okay. So it means what? Two events E and F are independent if the joint probability P of E intersection F is same as P of E into P of F. Okay. So two events that are not independent, we can call them as dependent. Okay. So what are independent events? So the actual meaning is that the occurrence of one event does not affect the other event. Okay. So because of which you will have P of E given F is P of E, which reduces to this condition that P of E intersection F is equal to P of E into P of F. Okay. Fine. The definition I hope is clear for everyone.
Yes,
Okay.
ma'am.
Okay. Now multiplication rule for two independent events. So you know that, so this is not just the definition here. So it is if it is definition, usually it is an if and only if condition. What is meant by if and only if? So we say that two are independent if this is happening. Okay. And if this is happening, that it means if this condition is there, then also you can say that two are independent. So both way it is true. This way as well as this way. In both directions, it is true. Okay, so this is the multiplication rule for independent events. Okay, now let's look at an example. So this is a rolling a dice twice, the same example we considered earlier. So we know this is the sample space. Now we have the following events. Okay, so the first event is the first outcome is a 5. The second event is the sum of outcomes is 9. And the third event is sum of outcome is 7. Now the question is, are the events E1 and E2 independent? Are the events E1 and E3 independent? Okay. So how do we check independence? So if you have to check E1 and E2 are independent, what is that we need to check? What is
P
that
of
we need
E1 intersection E2.
is equal to?
P of E1 into E2.
So this is what we need to check. Same way, here what is that we need to check? P of E1 intersection E3. Is this equal to P of E1 into P of E2? Okay, so this is what we need to check. So from here, first of all, what are the elements in E1? First outcome is a 5.
5-1, 5-2, 5-3, 5-4, 5-5, 5-6.
Yes, 5-1, 5-2, 5-3, 5-4, 5-5, and 5-6. Okay. Now, what are the entries in E2?
3, 6,
3, 6,
4, 5, 5, 4, and 6, 3.
What about 7? What are the outcomes for E3?
1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1.
Okay. Now, what are the entries in E1 intersection E2?
5, 4.
Only 5, 4. So, what is probability of E1 intersection E2?
1 by 36.
1 by 36. What is probability of E1?
6 by 36.
What is probability of E2?
4 by 36.
So, probability of E1 into probability of E2 is 24 by 36 into 36. Is this same as 1 by 36?
No, madam.
So, you can see that they are not equal. If they are not equal, then what is the answer?
Dependent.
E1 and E2 are dependent. Okay, so let's look at the next case. So now you have E1 and E3 are independent. They are asking whether they are independent. So now again the same process we have to do. So here, what are the entries in E1 intersection E3? E1 intersection E3.
5, 2.
5, 2. Only 5, 2. Okay. So here you have probability of E1 intersection E3 is 1 by 36 again. We already know probability of E1. So what is probability of E3?
6 by 36.
6 by 36. So probability of E1 into probability of E3 is 6 by 36 into 6 by 36. So which is 1 by 36. So this is same as probability of E1 intersection E. Now what does this imply? E1 and E3
They
are
are independent.
independent. Right? So in the first case, they were not equal and hence dependent. And in this case, they are equal and hence independent. Okay, clear? Okay, so let's look at another example. So consider again the experiment of randomly selecting one card from a deck of 52 playing cards. Okay, so you have all these 52 playing cards. Now the events are defined as follows. Okay, so E1 is the event of having a face card. What is mean by face card?
Jack, Queen, and King.
Okay, so these are the face cards. What about queen, you know, right? So how many queens you know?
4.
You have 4 queens, right? So I don't know how to write it. Maybe queen 1, queen 2, or how to write. So Q, you have 2 and you have queen 3 queens. You have 4 queens, 2 red and 2 black, right? And diamond, how many you know?
13.
13.
Diamond, you know, there are 13, right? Starting from A, and then you have 2, 3, up to 10, and then J, Q, K. Right? So you have 13 cards. Okay? All right. So now the question is, are E1 and E2 independent? Are E2 and E3 independent? Okay, so what is your answer? So first of all, here again the same conditions we need to check. So for that, we need to see. So here in the first case, you see in E1, there are totally 3. So here there are 4 and here there are 13 outcomes. So we need to look at probability of E1, E2, probability of E3 and their intersections. Right? So first of all, what is probability of E1?
12 by 52.
Sorry, 1. Why 1?
12 by 52, madam.
12 by 52.
Yes,
12 by
because
52.
we have 12.
Okay, just a
Okay,
case
sorry.
card. Okay. So 3 into 4 by 52. So you
Hmm.
have 12 by 52. Yes. Now what is probability of E2?
4 by 52.
4 by 52. What is probability of E3?
13 by 52.
13 by 52. All right. Now, what is probability of, maybe first, what is E1 intersection E2? Maybe let's put it like a heart and this is a diamond one. Okay, and this is your diamond one. So what is there in the intersection?
4 by 52.
So, no, how many elements are there in the intersection?
4 cards are there, madam.
4 cards, all the 4 cards, right?
Yes.
You have Q1, Q2, Q3, all the 4 cards are there in the intersection. So you have Q1, Q2, and you have Q3, Q4. All these cards are there in the intersection. So it means probability of E1 intersection E2 is again 4 by 52. Okay, fine. What is probability of E1 into probability of E2? 12 by 52 into 4 by 52. Is it same as 4 by 52?
No.
Obviously not. So E1 and E2 are
Dependent.
dependent. Okay, now what is there in E1 intersection E3? What is there in E1 intersection?
3.
You have the 3 cards J, Q, K. Right? So you have P of E1 intersection E3 is 3 by 52.
52.
Now, what is P of E1 intersection, sorry, P of E1 into P of E3? P of E1 is 12 by 52. P of E3 is 13 by 52. Is it same as 3 by 52?
Yes.
Yes? Is it same?
Yes, madam. Yeah.
Oh. So here this is P of E1 intersection E3. So this implies E1 and E3 are independent. Okay. Fine. So this question is also clear for everyone, right? Okay.
Yes,
So
madam.
now we are going to look at some properties of independent events. Okay. So what are the properties of independent events? So the first property we are going to see here is if E and F are independent events, then E and F complement are also independent. What does that mean? So here, suppose, let us say that the event E and F, they are not dependent on each other. So the F complement should also not affect E, right? So intuitively, you can see that happen, right? Intuition, can you all feel that this should happen? Or the intuition is not very clear? If you have the intuition, then it is a good way to go about. Yeah? Can you feel it from intuition that this should happen? Anyway, we are going to look at the proof. Why it should be true? Is that making sense? Just by understanding or imagining it? Okay, so maybe we'll see some also after the proof. So for now, let's go with the proof. Okay, so here we'll first try to understand how to explain E using both this two sets E intersection F and E intersection F complement here. Okay, so first given thing is that E and F are independent. Okay, so now E and F are independent. That is given to us. Now we are going to express E as E intersection F union E intersection F complement. Why is that so? So suppose let us say this is your E and this is your F. Okay, so this is your E and this is your F. Now what is E intersection F? So your E intersection F is this. So this is your E intersection F. Right? Okay. Now what is E intersection F complement? Your E intersection F complement. So all this together is E intersection. What is F complement first of all? So this is your F. If this is your F, everything outside of F is actually F complement, right? So all this is F complement, right? From this, what is E intersection F complement? Is this region? So this is E intersection F complement, and this is just F complement. So what are the sets E intersection F and E intersection F complement? That is clear for everyone, right? From the Venn diagram. And now E is E intersection F union E intersection F complement. That should also be clear. So E is the union of this and this part together, right? So first of all, this expression, is it clear for everyone why E can be written in this way? Is that clear for everyone? Yeah. Okay. So now from here, the next step is that now E intersection F and E intersection F complement. Are they mutually exclusive? What is meant by mutually exclusive? What is meant by mutually exclusive? E intersection F, E intersection F complement. Is there
But if
anything
we
in the
are doing the intersection, then it's 5. 5 means
this means
no.
that yeah, no elements are there. So E intersection F and E intersection F complement are mutually exclusive. So this means that if they are mutually exclusive, so if you have P of A union B, where P of A intersection B is empty, then what will be the formula for A union B? Simply P of A,
Probability of A and probability of B.
right? So you know that this is there. So if this condition is there, we can apply it here. So what is probability of E? Probability of E is simply P of E intersection F plus P of E intersection F complement. Is this fine for everyone up to this?
Yes, ma'am.
Okay. Now, given that E and F are independent, if E and F are independent, what do you know? P of E intersection F is equal to
Probability of E.
into probability of F, right? So in that case, I can replace this P of E equal to P of E into P of F plus P of E intersection F complement. Okay. All right. So now I'm going to bring all these terms to the other side. If I'm bringing all these terms to the other side, what will I have? P of E. So this term I'm going to bring it here, minus P of E into P of F is equal to P of E intersection F complement. Okay, so this means that my P of E intersection F complement is P of E into 1 minus P of F. Okay, so now what is P of A complement for any A? It is 1 minus P of A, right?
Yes, ma'am.
So in that case, what is 1 minus P of F?
P of FC.
So it is P of.
Complement of PF.
So you see that P of E intersection F complement is equal to P of E into P of F complement, which implies E and F complement are
Independent.
independent. All right. So you see that if E and F are independent, then E and F complement should also be independent, right?
In the
So
same way, F and E complement will also be independent, madam.
yes, yes. The proof is just exactly the same. Just you have to start with P of F. That's all.
Okay.
So you just have to interchange the positions of E and F. That's all. Okay. All right. So now we got that P of E and F are mutually, E and F complement are also independent. So not mutually, so they are independent. Okay. So it means what? If the occurrence of F does not affect E, so the not occurrence of F also should not affect E, right? So whether F happens or not, so what is the intuition behind E and F are independent? What does that mean? So whether F happens, so that is the event of probability of E, or F does not happen, so that is F complement, E will not be affected. Right? That is the intuition, right? Whether F happens or not, it does not matter. F does not matter to E at all. Okay? So that is what is the meaning of being independent. P of E intersection F is simply P of E into P of F. Same way P of E intersection F complement is P of E into P of F complement. Is the proof as well as the intuition making sense for everyone?
Yes,
Yeah?
ma'am.
Okay, good. Okay, so let us see some examples now. Now, suppose that E is independent of F. Okay, so first E is independent of F is given. Also independent of G. Okay, so you have P of E and F are independent, and then E and G are independent. Is E necessarily independent of F intersection G? So the thing is that they are saying P of E intersection F is equal to P of E into P of F. Okay. So now also it is given that P of E intersection G is P of E into P of G. This is also given. Now is E necessarily independent of F intersection G? So is this true? Given this, is this true? This is the question. Okay, we only have the above information. With this, is this true? Okay, so we are going to try to understand whether this is possible or not with an example, which we have already seen. Okay, so we have seen the case where two dice are thrown. Okay, when the sum of 7 independent of the first throw. So here, let's go back. So when the sum is 7, it is independent of the first outcome. So P of E1 intersection E3, you saw that E1 and E3 are independent, right? So whether the first outcome is 5, 1, 2, 3, 4, or 6, or anything, whatever is the first outcome, you will be getting the same answer. So here note that in general, the first outcome does not affect E3, right? So if this 5 is not anything special, instead of 5, if it is 1, 2, 3, 4, or 6, still you can observe that. So P of E1 into P of E3 is again 1 by 36 only, right? So that is what here they are using, that getting a sum of 7 is independent of the outcome of the first row. So this line, is it clear for everyone? That sum of 7 is independent of the first row. Okay. Now similarly, getting a sum of 7 is independent of the second outcome as well. Okay. So same way, if you consider what is the second event, given the second event, then also you can see that the same logic will work, and then you see that this is also independent. So it is independent of the first outcome and the second outcome as well. So how to write this? So let E denote the event that the sum of the dice is 7. Let F denote the event that the first die equals 4. Okay. And let G denote the event that the second die equals 3. Okay. Now what is F intersection G? F intersection G is the event of first row is a 4 and second row is a 3. Correct? First of all, here before going to the next part, first let's try to understand what is happening here. So for E, what are the possible outcomes of E? What are the possible outcomes of E? We have already seen that, right?
Yes, ma'am.
So these are the possible outcomes of E. Right? Now, what are the possible outcomes of F? So you know that again you have 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. Same way, you have 6 outcomes here as well. Second one is 3. So 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3. So you can clearly see that probability of E, probability of F, probability of G, everything is 6 by 36. Correct? Also, probability of what is E intersection F? 1 by 36. What is probability of E intersection G? Again, 1 by 36. So you can see that probability of E intersection F is equal to probability of E into probability of F. Is that correct? The first one, is this condition satisfied? So here also you have 1 by 36. Here also you have 1 by 36. Correct? Yeah. So maybe if you want,
Yes, ma'am.
you can write it in this way. 1 by 6 into 1 by 6. Okay. So same way, probability of E intersection G is probability of E into probability of G. So 1 by 36 equal to 1 by 6 into 1 by 6. So what is that you observe here? You observe that E and F are independent. And then E and G are independent. These two things we observe. Now, the thing is that, is E independent of F intersection G? Now, what is there in F intersection G? What is there in F
Only one.
intersection G?
4, 3.
Only 4, 3. Okay. So now the question is F intersection G independent of E? So what is the question? So P of E given F intersection G should be same as P of E. So now what is P of E given F intersection G? What is P of E given F intersection G? So this is the only event. Now the if given is this, so your sample space is just 4, 3. And your E is the sum of the dice is 7. So what is the probability? You have only one element out of which, so this is the total sample space. So in that sample space, is there a probability that the sum of the entries is 7?
Yes,
So what should be the probability?
1.
1. So if it is 1, obviously this is not equal to probability of E. Right? So this means you know that E and F intersection G are not independent. So from here, you can answer this question that E and F are independent, E and G are independent does not guarantee that E and F intersection G are independent. Okay, so the answer here is no. Okay, so we have seen this through this example. Okay, so is this example clear for everyone? First, we observe that E and F are independent, and we observe E and G are also independent, but E and F intersection G are not independent. Okay, so independent of 3 events is not very easy to explain in terms of formulas. Okay, so when you are going to use in terms of formulas, you have to be very, very careful. Just for 3 events itself is quite complicated, right? So so multiplication rule, in general, you were able to extend it very easily. But multiplication rule for independent event, you cannot just like that write this condition. Okay, you have to be very careful while writing multiplication rule for independent events. So you have all these conditions. E, F, and G are said to be independent if all the 4 conditions are satisfied. So P of E intersection F intersection G is first of all P of E into P of F into P of G, and all of them should be independent with each other. E and F, E and G, F and G, all of them should be independent with each other. Then only we can say that E, F, and G are independent. Okay, fine. All right. So in general, for probability of independent events, the probability that all occur equals the product of their individual probabilities. Okay, fine. So this is the independence of 3 events, definition for independence of 3 events. Okay, so now let us look at an example here. There are 3 packs of cards and a card is randomly picked from each of the packs. Okay, find the probability that all 3 cards are red. So this is a very easy question only. Everyone please go through it again. I have also started with a hint to start answering the question also. You are having 3 packs of cards. Okay, so first pack, so pack 1, pack 2, pack 3. In each pack, you have 52 cards. Okay, and a card is randomly picked from each of this pack. Find the probability that all the 3 cards are red. How can you do this? Now, you are defining the EI to be the event that the ith card is red. Okay, so this is the first card, second card, third card. So EI is the event that the ith card is red. How can you do this? How can you solve this? This is a very easy question only. Think and tell me the answer. Yeah,
And it is the
See, E1 is the E1.
78C3 divided by
Don't go to combinatorics. So come
Okay.
here. So use the properties which we just saw here. So E1, E2, E3. First of all, intuitively, do you think they are independent of each other? Taking one card from pack 1, does it affect taking the option for taking card from pack 2 or pack 3?
no.
Okay, so this means that E1, E2, E3 are independent events,
Yes.
right? If they are independent events, now you want to find, so what is that we need to find? First of all, first write that what is that we need to find? Find the probability that all the 3 cards are red. Now, if EI is the event that direct card is red, what is that we need to find? P of E1.
Even intersection E2, intersection E3.
This is what we need to find. And already we know that they are independent events. If they are independent, what do we know? It is equal to
Even
Probability of E1 and 2.
right? So what is the probability of picking a red card from a pack of 52 cards?
26 by
26 by
50.
52.
So it is 26 by 52 into 26 by 52 into 26 by 52. As simple as that. So 1 by 2 into 1 by 2 into 1 by 2. So 1 by 8. Is it straightforward? Very easy, right? Yeah. Okay. Fine. Okay. So, yeah. Oh, there is this, now the next part is the important part. I guess so far all the topics were clear for everyone. Now we move to the next one. So this explanation I have already given. Why P of E is equal to P of E intersection F plus P of E intersection F complement. This part I have already explained using the Venn diagram I explained, right? So this part I have already explained. Now here they are again using the multiplication rule. Okay. So now P of E intersection F is P of F into P of E by F, E given F. And P of E intersection F complement is P of F complement into P of E given F complement. So just writing the multiplication rule for each of this. Okay. So this is law of total probability. Now this can be expanded to K entries, any number. Okay. Suppose you have F1, F2, Fk, which are mutually exclusive. Remember that the condition here is that E and E intersection F and E intersection F complement are mutually exclusive. Okay. So here, suppose that we have F1, F2, Fk. We have all these are mutually exclusive and exhaustive. So what is mean by exhaustive? So it means that exactly one of the events must obviously happen. It means the union is the whole sample space. Okay. Then for any event E, P of E is P of E given F1 into P of F1 plus P of E given F2 into P of F2 plus etc. P of E given Fk into P of Fk. Okay. So here F and F complement are mutually exclusive. That is what is used here, not E intersection F. Sorry, I gave the wrong hint here. So F and F complement are mutually exclusive. So instead of F here, now you have F1, F2 and F2, up to Fp. Right? And exhaustive in the sense that what is F union F complement? It is your entire space. Right? So this means that they are exhaustive. Any one of the events must occur. Right? Either F should occur or F complement should occur. Okay. So now instead of F and F complement, they are using F1, F2 and so on. Okay. Is it making sense? Yeah. All right. Now we'll see an example to understand how to use this particular formula here. Now, an insurance company believes that people can be divided into 2 classes. Okay. So what are those two classes? Those who are prone to have accidents and those who are not prone to accidents. Two classes. So the first class we are referring to as A and the second is A complement. Okay. Now the data indicate that an accident prone person will have an accident within a period of 1 year. Okay. So within a 1 year period with the probability 0.1. Okay. So if there is a person who is accident prone, the probability that he will have an accident within 1 year is 0.1. So what is this probability actually? So here, what is this statement saying? Can anyone try to explain? Use in terms of probability. Suppose let us say E is the probability that a person has, even that the person has an accident within 1 year. How can you explain this statement using probable in terms of probability? Anyone? Can you give a try? What is this line telling? What is given? An accident prone person is given. The person is accident prone is given. And then the probability that the accident happens within a year is 0.1. So what is this line saying? What is this 0.1 representing? What probability is it representing?
Probability of
Probability of
accident of that person in 1 year.
yeah. So you have A complement E. Can you use these events to explain it? See what is given here? Given
P of A.
accident. So this is given. So if this is given, accident prone person is A. The probability that the accident happens within 1 year. Okay, so this is E. So what is this representing 0.1? Probability of
A intersection E.
A.
not, see, not and. This is given.
Probability of A.
No, I have used the word given.
Give.
So you should understand from that.
Probability of
right?
E
E
given
given
A.
A.
Exactly. Okay,
E
so
given.
the 0.1 is probability of E given A. Okay, if you have the word and, then only intersection should come. Here they are saying an accident prone person will have an accident within 1 year. So already the person is accident prone, that is given. And then you are having this condition that, and then the probability is 0.1 for accident to happen within 1 year. So this is P of E given E. Okay, very good. The next line, the probability for all others is 0.05. So what does that mean? For all others, so for A, it is 0.1. For all others, it is 0.05. What does that mean? So the
A
same thing.
complement.
Exactly. E probability of E given A complement is 0.05. Okay. So the probability that the accident happens within 1 year for an accident prone person is 0.1. And for a person not in accident prone zone is 0.05. Okay. So what are the things given? P of E given A is 0.1. P of E given A complement is 0.05. And then you are given, suppose the probability is 0.2 for a accident prone person. So probability of A is 0.2. So probability of A complement should be 1 minus 0.2. So 0.8. Okay. So these are the given things. So what is given here? Is that clear for everyone? Okay. Now what is that they are asking? What is the probability that a new policy holder will have an accident in the first year? So it means they are asking what is the probability of E. Right? We want to find probability of E. How can we find probability of E? What is that we saw just now? How can you use that here?
P of A multiplied by P of E given A plus
P of A into P of
multiplied E given A plus P of A complement multiplied by P E given A complement.
very good. So now do we know all these values? What is P of A?
0.2,
What is P of E given A?
0.1,
What is P of A complement?
0.8
What is P of
into
A?
0.05.
Yes. Okay. So this is the answer. You can simplify and check. This is the answer for P of E. So this question, what is given and what is it we need to find and how to use the formula? Is it all making sense for everyone? Yeah? Okay.
Yes, ma'am.
See, this Bayes rule is kind of a fancy thing to be asked in interviews. Okay, so if someone asks, do you know probability? Then they give a question from Bayes theorem. So it's kind of a fancy thing to ask from probability. So it's good that you all know what is Bayes rule. It's very simple. If you have understood so far, Bayes rule is not a big deal. Okay, so what is this Bayes rule or sometimes called Bayes theorem saying? So suppose we are now interested in the conditional probability of F given E. Okay, so here, what is probability of F given E? This is what we want to know. So this is a probability. This is the formula, right? For P of F given E, P of F intersection E by P of E, right? So from definition, P of F given E is P of F intersection E by P of E. Now what is P of F intersection E? It is P of E by F, E given F into P of F. This formula, you know. And then P of E, you can write it. So both these formulas, you know. So this is equal to this is equal to this. Both these things, you know. So just a substitution of this. So this is Bayes rule, as simple as that. So if you have followed so far, Bayes rule is nothing. It's very easy. Okay. Now let's try to do a problem based on this. The only thing is that you should be able to understand what is given in the question. So whether it is a Bayes rule problem or not, that if you identify, then you can easily use the Bayes rule and answer. Okay. So now the question is the same. So the first part is exactly the same. So this part is exactly the same. So P of A complement, P of E given A, P of E given A complement, all these are same. Now the question is, if a new policy holder has an accident in the first year, okay, so this is the condition given to you. So what is the given condition? Given is your E. What is the probability that he or she is accident prone? So that is in A. So what is that we need to find? Can you tell? Probability of
A over E, A given E.
exactly. We need to find probability of A given E. Okay. So now for probability of A given E, what is the formula? What is the formula for probability of A given E?
Probability of A intersection E
Yes.
Probability of
given divided by probability of E.
Probability of
A intersection E by
probability of E. So in the previous problem, we have already computed probability of E. So this is already computed, right? Now the only task is to find what is probability of A intersection E. So probability of A intersection E, what is the formula? Which we just saw here. So this formula,
E given
probability
A.
of
E given A.
what is probability of E given A?
0.1,
And probability of A is?
0.2.
So probability of A given E is, I don't know whether you have calculated the previous one. The previous one, the
0.02.
0 point, so this one is 0.02. The previous one, did you calculate? So it says
0.42,
0.04 to 0.06, right? So it is 0.02. So probability of A
0.0
given E is 0.02 divided by
0.06.
so 1 by 3.
1.
Okay. Good. So I try to cover all the topics as much as possible by giving at least one example in each case. So in the next session, definitely we will see lot of examples. So in the next session, you have the doubt session. So there, I'll try to solve many problems in each case. But in this session, I hope you all know at least each topic clearly. And I hope you all understood all the topics and the formulas also you understood, I hope. Yeah. Any questions or from what we have done so far? If you have doubts in some specific questions, yeah, we have the next session on Sunday. That time we can discuss specific question doubts. If you have any questions from whatever I have done in today's session, please let me know. Okay. Okay, then thank you everyone. See you again in the next session.
Yeah, thank you, ma'am.
Thank you.
Thank you so much.